right. How are you guys doing? Doing all right? All right, so last week we talked about sedimentation. Um, we covered kind of intro to drinking water, oriented ourselves to what does drinking water treatment typically entail, and what might that look like. The first thing is to use gravity, right? So we're in sedimentation. We worked a practice problem. We took a look at, how quickly are these particles going to settle, and will this particular reactor remove them? So today we want to go from there and take a look at how do we make them stick together more, and what is the result of that afterwards. So just a couple quick notes on sedimentation itself. I think I touched on these, but just to be clear, and then a couple little tangents here. For sedimentation design, we can think of the area of the basin, right? We talked about how the area of the basin is very important, and that had to do with the fact that we have some height to travel in some time to travel in it, right? And I said that with the hydraulic retention time, theta, being the amount of time the water is spending in the reactor, the height of the particle from the top of the reactor by the time it reaches the end, that's the distance it needs to travel per time it needs to travel. That's essentially our critical settling velocity, right? By definition. And we also said that we could relate that in terms of theta being V over Q, which is the same thing as saying in terms of a reactor where we have a length, a width, and some height, right? Or maybe a better way to write that to be consistent with what I've done in the past, to say this is height, and we have some imaginary depth here, right? And then this term would be the width. So regardless, we have an area. This would be the length times the width. And so the volume we could express as some area of the basin times the height. That also holds true if we have a cylindrical system, where we have some R, and we can imagine some height coming out of the page in this time. So if we imagine some system like that and say this is the height, and we have some area of the basin would be pi r squared, we could say that still the critical settling velocity is still defined as height over the area of the basin divided by the height, and all of that divided by Q. Right, so I wanted to be very clear that it doesn't really matter if the area of the basin is length times width, or if the area of the basin is pi r squared. Whatever the area of the basin is, that's present in our derivation when we say then V naught, these H's will cancel, and we're left with 1 over area of the basin over Q. Of course, we can flip that and say this is Q over the area of the basin. Okay, so I explained that last time. I just wanted to make sure it's very clear. It doesn't really matter the style, the geometry of the basin. It can be rectangular or cylindrical. In both cases, that all applies. That also means that we could potentially increase the rate at which we're settling things and have a higher efficiency settling process if we add in some shelves, because it's like adding in free area. I say free, technically there are some challenges to doing this in a manner where you can scrape away the particles effectively and manage your system in a way where you're not going to kick up the particles and resuspend them and send them down through your process accidentally. So there are some challenges here to doing it well, but just as a side note, there are such things as high rate settlers, and in certain conditions that can be pretty useful, because it's kind of like you just multiplied the area of the basin, you added 3 more area of the basin. So if this is approximately the area of the basin. Just have it tilted slightly. You have one here. You know, now you have essentially 4 times AB. That's great. Okay, the last little tangent I want to spend on the sedimentation, and I think maybe I mentioned this, is an upflow design. It's kind of all or nothing, where your water is flowing over the top somewhere in a kind of trapezoidal system like this. And right at the top, the velocity term, that's going to be our critical settling velocity, because you have to meet or exceed that in order for the particles not to escape over. And that if we shape it this way, we might have a strong velocity term this down here and a smaller one up towards the top because it's spread out over. So these are occasionally used. They're pretty much more all or nothing. It's either 100% or 0% removal. And in situations like this, one thing that may help is if we go against our assumptions. We're assuming that the particles are not sticking together during this process. They're just discrete. Nothing weird's happening. But in reality, usually they, especially if we're designing it, we'll see in a moment, to stick together. And that would actually be pretty common. And then what you would have is sort of a blanket layer of these particles starting to come together right here where they were meeting, not quite going over. And then they'll gather into larger particles and slowly start settling out. It'll almost like form a blanket, and then it'll sort of sweep through the rest of the water, and that can then be a benefit. So there are some interesting things in practice like that. They're not super common, but I just wanted to say those. All right, so last portion of the kind of sedimentation design itself, and this one is a little more relevant to the types of stuff we'll work on, and that is what happens if we don't have full removal. Again, I think I mentioned this. I just wanted to make sure this is very clear and well drawn out for you. If we consider some portion of the particles, let's say the particle at the top, let's say we have a condition where this Vs is clearly not meeting the bottom in time, right? So this condition, Vs is less than V naught. The actual sedimentation velocity is slower than that critical one where everything would be removed. Well, you do see that at some point, at some distance down here, a particle will actually be removed, right? If we find that particular one, that means we have some height here, some amount of the water column, some portion of it that is escaping, but the rest of it from basically here on down should be removed, given that condition. And the geometry works out very cleanly here because we're dealing with these kind of right angle triangles and all that. And so the same proportion ends up over here. We could say this is the proportion that escapes. And this proportion, and it doesn't really matter which side you draw it on, but this proportion was removed. So it turns out that you can kind of look at it in terms of the height, and the time that the particles are staying in here doesn't change. It's still theta. So the height can correlate directly with the velocity. So we could say that the height for removed divided by the height for escaped is going to be, the same thing, well, really is the same thing as the portion of the velocity here for the let's see if I'm getting this right. So this would be the stuff that's removed. That should be Vs, I think. Let's see. No, that should be the V naught. Yeah, no, that's right. I have it right. Okay, over V naught. And this is where we can then define our system as some percentage of the particles removed will have some percent removal that's equated to the Vs divided by V naught over 100%. Now, I think that I'm second guessing myself right here, just the way I'm defining it. The bigger picture here is that if V naught is all of them removed, and Vs happens to be some part of them removed, that part divided by like the total removal would give us the right answer here. So it sort of feeds into that, even if I have this explanation slightly off, because maybe we need to look at the height divided by total height. I think that might be a little more accurate. Okay. At any rate, this value, the percent removal, it's just proportional to the difference, that ratio between the actual versus the critical settling velocity. And of course, you could imagine a situation where you put in some numbers and you have more than 100%, but that's not realistic. So, you know, just to remember that you can't have more than 100% of something removed, right? So if you have full removal, you have full removal. You don't have 1,000% removal. Okay. All right, so that's sedimentation for you. Next up is this coagulation. And so we're going to talk about dosing a coagulant. What is a coagulant? What does it do? How does it work? And then from there, we can move into, all right, now that we have this in here and it's going to cause the particles to stick together, how do we control a system to allow these particles to stick together by design and know that we have some outcome, and how do we deal with that mathematically? So that's going to be coagulation, then flocculation. Or flocculation, we are giving the particles time to stick together. Then we've got larger particles, and then we'll revisit what we just, I mean, we don't need to revisit it, but then we go through sedimentation again, and what we just learned applies again to these larger particles, right? Okay, so it's always good to think about what are we aiming to treat. You know, at the very beginning of the class, I said we've got some stuff inside some water, or you know, some media, some other stuff inside stuff. And in this case, it's worth taking a moment to think about, well, what are these particles and how big are they? What are some common things we might know about that we can relate to the particles that we're really trying to remove. So the last problem from last time said we had 0.01 millimeter silt particles. So that's you know, a soil particle that's smaller than a sand grain, a little bit larger than a clay particle, somewhere kind of between, right? So that's and 0.01 millimeters, that's going to be 10 micrometers. So this is the size we were looking at in our example last time. So you can look at this and say, okay, yeah, I can see visibly raindrops with my eyes. Perhaps, you know, if we look at what's visible with the human eye, maybe you can get down to the mist particles, maybe even large fog particles, however you define that. You know, most human hairs, apparently there are some that are small enough that you can't really see very well. So you can kind of get some idea, right? What is the size of the silt particle? Maybe just barely could see that an individual particle that we were talking about last time. Probably not really. We then have bacteria that are typically anywhere to 10 to 100 times smaller than that, or I guess up to that size and possibly down to less than a micrometer. We've got algae particles, or algae cells, which would, you know, maybe act like a particle. Some of them are larger that you can maybe see. Most of them are going to be small. We have these Cryptosporidium and Giardia cysts. These are what we might call parasites, or one type of parasite. They are not bacteria, but they're still single-cell organisms, and these two in particular are pretty infectious. These are, if you recall from your biology, this would be eukaryotic cells, so they have a cell wall, they can protect themselves a little better from the environment, but they're, you know, kind of pathogenic single-cell organisms, a lot similar to a bacteria. And then we have viruses way down here about 100 nanometers or smaller for the viruses. So at least at Earth's gravity, most of these things are not going to settle very well. I mean, we can see that maybe, just based on our example before, maybe some of these larger particles would settle. You know, we could have sand grains somewhere up here. Those should settle. Maybe larger soil particles than what we did last time, at least in that particular example, would settle. But there's no way in the world a virus particle that small is going to settle from just gravity and sedimentation. You can technically cause viruses to settle in a centrifuge if you ramp up the speed high enough. So you're inducing artificial gravity, get like 10, 20 Gs, something like that. Then over some time, you give it enough time, that same sedimentation process will happen. So it's possible, but you know, there's a big challenge if you want to do sedimentation, but let's say you're on the Death Star and you don't have very good gravity there, right? So you might have to think about creative ways to treat your water if you don't have gravity. Okay, or if you were somehow living on Jupiter, maybe sedimentation's all you need to do. All right, anyway, what about this coagulation? So when we talk about particles floating around in water, we use a word called stability, like they're stable or they're not stable. And what we're really referring to is how likely are they to stick to something else, whether that be the wall, whether that be the neighboring particle, or not. And so we say they're stable if they kind of have a force field of typically electrostatic repulsion, preventing them from getting too close and getting stuck. So when they get stuck, then they tend to aggregate into larger particles, and then they tend to fall out of solution, sediment. So that's the stability means they are going to continue to be free-floating individual particles. So the terminology is a little funny, but this means they are continuing to stay suspended, essentially. So suspended particles are similar to something that's dissolved. They're just floating around in the water, but they're not actually dissolved because it's a solid, right? So the colloids, you might hear as a term, or these small particles that are stable, you know, are an interesting in-between point between some solid thing and something that's dissolved. Okay, so then if we destabilize the particles, that means we've removed their little force fields and allowed them to stick together. And if they get close enough, there's some other forces that take play. We call these the van der Waals forces that actually are quite sticky. So if you've ever seen or heard of the fact that little geckos have little sticky feet pads, or maybe little frogs, and they can climb like a very clean glass sheet, doesn't matter how smooth the surface is, they can climb it. They're actually using those van der Waals forces. Their little foot pads are designed in such a way where the molecules get really, really close to the surface so that they can make use of these really short-range attractive forces. It's, you know, there are several different forces in there. Some of it's magnetic, some of it's the electron clouds, not the charge, but the clouds meeting each other tends to stick. There's several of them, and they just happen to be pretty strong if you get close enough. So the design of our coagulation is to cause particles to get really close together. So the electrostatic, that's going to repel particles. This is our plus or minus charges, right? The you know, and you can think of static electricity, right? You've done that with like a balloon in your hair or whatever. You know, you've seen that kind of thing. Charged stuff will interact. You know, if you have a spigot of water, just a stream of water flowing, and you charge up a balloon, you know, rub it on somebody's hair or something, and you put it next to that water, it'll actually pull or push the water. I think it would normally pull the water because of some of those electrostatic interactions. So you've kind of seen that before. And then on a small scale, particles typically in water end up with a net negative surface charge. There are several reasons for this. There's some acid-base chemistry. There's, in the sake of, like in the situation for clay particles or something like that, there'll be like mineral substitution stuff happening, some high sciencey stuff that cause a net negative surface charge on most aqueous particles. So that's just kind of a given. And given that, what ends up happening is you get two like charges and they're going to repel each other. But there's another feature here that causes this to be a bigger problem, especially in fresh water. So in pretty much any water, we're going to have some actual charged ions in solution. And the positive ions will be attracted to that surface and form some kind of a layer next to it. These are going to be free floating and diffusing around, but generally attracted to this area, so they're a little bit confined. And just based on thermodynamics, energy, charge balance, all that, it's favorable for them to be next to these surfaces. So you're going to have a positive charged layer of ions next to the surface, which will then in turn attract another layer of ions that are a little bit weaker, looser, they're kind of hanging around in different places, but net negative still in what we would call an electrical double layer. So in this way, and there's going to be some positive charges floating around because these are diffusing a bit, but you'll have this net double layer of electrons that really extends out that repulsion, because now you have not just the charge at the surface, you have a charge that has been communicated out into solution based on these ions. So that's part of the long range. What we want to destabilize the particles is to really shrink that, to remove that effect, so that the particles can get close enough to stick. Okay? So then, these van der Waals forces, you can think of the gecko. Is there a C there? I don't remember. We'll say there is. These are going to be essentially a function of 1 over radius to the 4th, or maybe even 1 over radius to the 6th, whereas the electrostatic is going to be 1 over radius squared, I believe. So you can see why the electrostatic has a longer range, and that's going to be repelling if they're both like charge, which is the typical scenario. Whereas the van der Waals, they're actually pretty strong attractive forces, but they really don't have some impact more than maybe a few nanometers into the water. So this means like maybe 5 nanometers you'll start feeling that. Whereas this electrostatic could be 30, 40, 50 nanometers out. We'll see some examples of that. So the question becomes, how do we interrupt this electrostatic repulsion? One of the things to note here is that osmosis creates a pressure gradient. Osmosis is the effect that you want, that a solution wants to balance the charged things throughout. So the lowest energy state would have a perfectly even distribution of all the charge, all the particles, all the stuff. It just wants a nice flat, no gradient kind of a situation. When you introduce a charged surface, it's pulling some of those charges to the surface, but that means you're kind of pulling them out of the middle, the rest of the water. So if you have very, very pure water, that pureness is going to sort of pull these charges away from the surface and extend that out further. If you have really, really salty water, it's going to say, oh, well, there's these charged particles everywhere. We don't really need to distribute them very much because they're just kind of everywhere. So it'll really compress that double layer. So one of the things you could think about is, well, let's just add a bunch of salt to our water, right? That'll clean it. That presents a new problem because we don't like to drink salty water. So we'll take a look at that in just a second. Here's just another description here. And you can imagine if there's some force, osmosis force, pulling this out, what you might end up having is this, and let's imagine for a moment there's a negatively charged surface here, right? This is your surface. It has a negative charge. So all these ions are happening. You see the double layer forming here. If you have this a very strong osmotic pressure pulling the gradient outwards, maybe you have a situation where it looks more like this, and your electrical double layer now is a lot longer distance out into solution than it was right here. Okay, and that would just be because you had more or less charged ions in solution. Okay, so very, very pure, clean water will have a longer electrical double layer. This is actually why hardness makes it feel like soap. If you have very, very soft water, it makes you feel like you can't get the soap off, because you have a bigger distance between your actual skin, the surface here, and anything else that's interacting with it because of this exact phenomenon. So as we'll see in a moment, if we were to have, let's say, a 2+ charge in here, that satisfies a lot more charge per space. So if we were to say we have this one occupying a 2+, then it actually satisfies this entire space in just one little spot. So it kind of compresses it. That's the same thing that's going to happen with hardness. Hardness is typically calcium 2+ and magnesium 2+. So if you start introducing this 2+ or even a 3+ type of thing, it's going to compress this because the charge is not occupying as much space. So that's one thing. We could also just add simply more charge to the solution, making it saltier in that manner. So there's a couple things happening here, and I'm going to show you on these graphs. They're a little small, probably hard to read. So I'm going to give you the overview and kind of walk you through what we're seeing. So let's focus on the larger one here first. And so the x-axis here is how much of a coagulant dose are we giving. So how much in milligrams per liter, how much salt are we adding of some form or another. So we'll say that's a dose of salt in some sense. The y-axis, this is the remaining or residual turbidity. Now that is a fancy term for saying how many particles are in there. So these graphs are essentially showing before we add anything at 0, we have 100% of the particles are sitting there in solution. Turbidity, that's a measurement for light scattering. So if I were to shake up my bottle real hard and there's a whole bunch of small bubbles in there, for a moment those bubbles are scattering light. And so you can't actually see through it right then until they clear. The same way, milk is mostly water, but there's suspended particles and you can't see through it very far because they're scattering all the light. Same thing with coffee. You can think about the difference between looking at a glass of coffee, if you were to put it in an actual glass, and a glass of tea. The tea is not very turbid. It's picking up that color, but it's not scattering the light. Whereas coffee's got a lot of small particles, it's scattering that light around, so you actually can't see through it very much. So that's turbidity. And so what they're measuring here is just light scattering as a way to tell us, are there still particles in there? All right, so with that, we add a bunch of sodium chloride up until we see the particles drop out of solution. And so we'll start with the sodium here, Na+. I'm just assuming this is probably sodium chloride, whatever. They're using a sodium salt. They have to add all the way up to about 10,000 milligrams per liter or 10 grams per liter before you see a meaningful change and they start to come out of solution. And then they fall out of solution pretty quick because you've destabilized them very well. So seawater, for a reference, is approximately 30 grams per liter of salt, as if we were to measure it in sodium chloride. So that's pretty salty. A third of the strength of seawater is probably still a little too salty to drink, right? So we don't want to do that. Sodium is pretty hard to remove back out of the water if we have it. Possible, but expensive. So that's not a good way to do it. So let's look at calcium. it actually takes 100 times less. So it only takes 100 milligrams per liter of calcium 2+. So we see that effect, that it's really compressing the, this double layer and making it so that it's a much smaller, smaller distance out into solution. Al3+ is even better, 10 times less than that, 10 milligrams per liter. So now we're getting to a point where we are at levels that, you know, might be quite reasonable to add as something to use in an actual treatment. And sure enough, aluminum sulfate, or alum, is actually our typical go-to. Sometimes there's like a iron chloride is another alternative, but aluminum sulfate, Al2, SO4, 3, that dissolves to give us Al3+, 2 of them, and 3 sulfates, which is SO4, 2-. So if we use aluminum sulfate, we're adding a lot of charge with a fewer amount of atoms or molecules. So these left figures are just a couple more demonstrations of that. In this case, it's like a distance on the x-axis in nanometers. And then on the y-axis, this is how much electric potential, millivolts, of that charged field that we can detect. And at the top one's looking at different dosages, 60 versus 600 versus 6,000 milligrams per liter of sodium chloride. And we can see us shrinking that double layer that way. How far into solution is our charge being sensed? Is this electric field being sensed? Or we can change the charge of the ion, right? So this would be like sodium plus for the Z=1, or calcium 2+, or aluminum 3+. So each of these is kind of saying the same thing. The more charge, the more it's shrinking that distance of the electrical field. So just wanted to kind of show you there's ways that people can measure this stuff, and it makes a really big impact when we do that. So when we think about coagulation, then what we're really dealing with is adding something that we can presumably remove after, or will be automatically removed as the particles are formed, that, you know, is not going to make our water too salty. And it's really just manipulating that charge for the most part. This is also why, if you are ever to look at where an estuary system, you've got a river flowing into the ocean, at the estuary, it probably looks kind of muddy. It's going to be somewhat turbid water, given that the river probably had a lot of sediments, a lot of suspended particles scattering the light. And then when you get way out into the open ocean, you will have reached a very salty condition that will have destabilized the particles. And so once you get past the area where they're all starting to aggregate and settle, it'll be very clear, ocean blue, like you can see pretty far through it. And this is exactly why. So there's going to be some cases, you know, if you were to go out to Mississippi, there's some area where it still looks pretty muddy because all of these processes haven't happened yet. Waves and things like that might be mixing the particles back into solution. But eventually you'll get to a point where the water is pretty clear because of the destabilization of the particles. All right, there's one other thing I wanted to mention. So these are kind of salt-based strategies, or some sort of just purely charge. And we're going to talk about ionic strength with that in mind. But there's one other thing that we can add, and that would be different kinds of polymers as a coagulant or an aid to the coagulation. So a polymer is a fancy word to say you've got a bunch of molecules linked together, right? So a DNA strand would be a polymer. Plastics are polymers. You know, the thread making my shirt here, there are polymers in that. You could even say that cotton is, you know, the fibers from cotton is some sort of form of a natural polymer. Cellulose is often thought of as a, you know, you can polymerize that and have that as a polymer. So this is just some fancy word to say, well, if you have two different particles, and you have some polymer that maybe has some charges on it, and who knows what shape that polymer takes, but if it has a couple charges or a couple spots where it likes to interact with these particles, it's sticky to them, and has a good chance of reaching them and connecting to them, then they could potentially bridge the particles and grab one with this hand and grab one with the tail or whatever, and now these particles are kind of attached and ultimately going to kind of stick together. So there's some polymer aids as a kind of a tangent, another way of making use of causing particles to stick together. So that's just a small tangent, and just to let you know a little more about practically what's used is typically a combination of adding something like aluminum sulfate and adding some polymers to improve that stickiness is pretty common. Okay, so then I'm going to give you a little bit of chemistry practice here with this part. And this is just a little reminder. You've probably seen ionic strength before. This is a term we can use to describe how many ions are in solution, or really some concentration that accounts for the charge. So it's the amount of charge in solution rather than the actual ions themselves. So our definition here for ionic strength is that it's equal to 1/2 times the sum of each concentration of a charged species times its particular charge squared. So a negative charge thing becomes positive with a square, so we don't have to worry about that. So we'll work this one together, and I'll give you another one as practice here in a moment. So the deal is we need to use molar units here. So we have to use moles per liter because we're quantifying the number of charges. So it's a number-based unit, and it's chemistry, so it's going to be molar. When we increase the ionic strength, that's probably the best way to understand how we're decreasing that electrical double layer, right? So it's not only the amount of charge to ions, but it also has to do with the strength of that charge. And this is a way to account for both. So let's take a look. If we have magnesium chloride, MgCl2, it's going to dissolve and form Mg2 plus and 2Cl minus. And so if we take 100 milligrams per liter, first we're asked to find the Mg2 plus, then the Cl minus, and use those to solve for the ionic strength. Now we need a periodic table to get the Mg and the Cl. Cl, I remember, should be 35.45 grams per mole for the molecular weight. Magnesium, I think, is something near 22, but I'll need somebody to check that, or I can do it real quick with you. Let me know if you find it before I do. .3. Okay, so take 20 seconds to think about how you would solve this. I'm going to solve it with you, and then I'll let you handle the next one on your own. so we want to get the molecular weight here. We have to find the molecular weight of magnesium chloride first, because we need a relationship to say how many moles per liter of magnesium chloride did we actually add. We could just say how many moles did we add in a given liter. So I'm going to find the moles per liter of this guy, and this we could consider has a 1 mole of that yields us 1 mole of magnesium, 2 plus, and 2 moles of chloride. So considering that will allow us to understand how many moles per liter of each of these did we get. So that's why we needed the atomic weights for magnesium and chloride. So we get a molecular weight of 95.2 grams per mole for MgCl2. So then we're going to take the 100 milligrams. I'm going to just go ahead and rewrite that as 0.1 grams per liter of MgCl2. And I'm going to essentially divide that by the molecular weight by multiplying by just the inverse, right? So 1 mole per 95.2 grams. I'm doing it that way because I needed to get rid of the grams, and that needed to convert it to moles, right? So this is moles of MgCl2 per gram of MgCl2. Okay, so that should give us a value. So if we do 1 divided by, give me 0.1. A value of, let's say 1.05 times 10 to the minus 3. Moles per liter. So that's the number of moles of MgCl2 per liter. So that means that our magnesium concentration, that was a 1-to-1. So that's also going to be 1.05 times 10 to the minus 3 moles per liter. And Cl2 is going to be 2 times that. Excuse me, I said Cl2, I meant Cl minus. Cl minus is going to be 2 times the 1.05 times 10 to the minus 3, which should be, what, 2.10. Okay, does that make sense? So if that's confusing, just double check that you're tracking what's happening with the chemistry conversions here. That hopefully is straightforward. So then we'll take the ionic strength to be 1/2 times the, the way I'll write it up, I'm going to write it up here to give myself a little more space. Should be 1/2 times concentration of Mg2 plus times its charge, 2 plus squared, plus the concentration of chloride times its charge squared. That'll be my equation for ionic strength. Right? That's the sum of the concentrations times their respective charges squared, all times 1/2. Okay, so then I have this 1/2 times 1.05 times 10 to the minus 3rd times 2 squared is 4, plus the Cl minus, which is 2.10 times 10 to the minus 3rd times its charge minus 1 squared is 1. And then I'm just going to pull up Excel to do that there. Is this making sense? Good. So hopefully that's fairly straightforward. So we're going to say Cl minus was 2.1 Mg2 plus was that. So we'll take our ionic strength to be 0.5 times the magnesium chloride times 4 plus the chloride times 1. Just leave it like that. And so our ionic strength then should come out to be 0.0315. So 0, 0. So it's basically 3.15 times 10 to the minus third. And if you notice, this is essentially molar units, kind of. It's going to be like a moles of charge per liter in some sense. So we could give it molar units, and that makes some sense. All right. So take a minute and work on this problem where you have not only magnesium chloride, but also sodium chloride. Okay, so now I'll get you the atomic weights here in a moment. Remember that I is 1/2 times the sum of the concentrations in molar units of each species times their particular charges squared. All right, so if I gave you all a quiz right now on the final answer, how good would you feel about that? Some of you pretty good? How many of you would not so good? Anybody sort of shaking on it? Okay. All right. And no harm on that. You know, I know that, you know, for example, the chemical engineers are bored and annoyed with me. And some of you are like bored, but also annoyed for a different reason, that you hate chemistry, right? I get that. So I'm just going to kind of take you through this real quick, make sure this is kind of the last real review part, I would say, just on the basics of chemistry for you here. And that is that there's two sources of chloride here, and they're coming from different of these dissolution reactions. You just need to combine them both properly, and you'll get your answer fine. So this is almost the same start as the previous question, except this time we have 0.05 grams. So 50 milligrams, I just convert that to 0.05 grams per liter. So that's what I put here. 0.05 grams divided by the molecular weight. This is going to give us the amount of moles of MgCl2 that I dissolved, right? So it's going to be, the reactions are going to be MgCl2, one of those going to 1 Mg2 plus and 2 Cl minus, just like we did. And then there's also going to be 1 sodium chloride dissolving to give us 1 sodium and 1 Cl minus, right? Those are the two reactions that we're dealing with. And each of these, we're going to assume they're salts, so they kind of completely dissolve. No weird stuff with the equilibrium. So then what I want to know is how many moles of magnesium chloride did I actually add. That way I can find the molar concentrations of these guys. So if we do this, got this in my Excel sheet, this comes out to be just half of what we did a moment ago. So this is 5.25 times 10 to the minus 4 moles per liter. That means that magnesium, which is only coming from this one source in a 1-to-1 ratio, right? If we look at 1 to 1, we can, by the way, if you really are feeling uncomfortable with this, you could do an equation to say 1 mole of Mg2 plus divided by 1 mole of MgCl2 and multiply this by 5.25 times 10 to the minus 4th moles per liter of MgCl2. This will allow you to cancel these guys and give you 5.25 times 10 to the minus 4th moles of Mg2 plus per liter. That's the explicit way of going about this. So follow the units if you need to. I tend to shortcut it myself on that 1-to-1 basis. So I'm elaborating here to make sure that's very clear. So that means Mg2 plus is 5.25 times 10 to the minus 4th. Okay, so there's one part. Now we also need our sodium and our chloride. I'm going to start with sodium. If we do the same thing we did a moment ago and say 0.05 grams per liter of sodium chloride, divide that by our molecular weight, which was 58.45 grams per mole. That should give us a value of 8.55 times 10 to the minus 4. Keep this out of my way. Moles per liter. Okay, so that gives us a 1-to-1 ratio of sodium chloride to going to sodium. So this one will also be 8.55 times 10 to the minus 4 moles per liter. And last, not least, Cl minus, we have two different things going into it, right? So this is the one complication I wanted to highlight to make sure you're building your confidence with chemistry so that we can do stuff like this. So the Cl2 here would be the contribution from both, right? So we would have 2 times the magnesium chloride concentration, because we get 2 moles of that per 1 mole of this. So that's where I'm going to say 2 times the concentration we found there, plus 1 times the concentration of NaCl. That would be the easiest way to think about it. So if you were putting in 2 different numbers in your ionic strength equation for chloride, you were doing something wrong. You have 1 concentration of chloride. Okay? So this comes out to be, when you do that math, I'll just go ahead and pull up the Excel sheet for you. That comes out to be, the chloride is 1.91 times 10 to the minus 3rd. And when you do your ionic strength, I'll write it out better in a moment, but the answer, the final answer would be 2.43 times 10 to the minus 3rd. Okay, and that, again, the actual ionic strength equation here would look like this. 1/2 times the concentration of Mg2 plus times, essentially 2 squared is 4, plus the concentration of your chloride times 1 minus 1 squared is 1, so I'm just going to ignore it, plus the concentration of sodium times its charge, 1 squared, so I'm going to ignore that as well. So that should be your the way to approach it. So if you were putting in some species here that didn't have a charge, like you put in sodium chloride, you're doing that wrong. If you put in something with 2 different chlorides, you're doing that part wrong. So just wanted to make sure that I call your attention to this kind of stuff, because I do know it's been a while for you civil engineers. Okay. If there's anything that's not making much sense here, happy to help you. Get with your classmates or myself. Make sure to clear that up. It's not the craziest chemistry that you ever have done. Okay, so here we come to flocculation. What I'll do is I'm going to go over essentially the basics to get us to the point where we can see where are we getting our rate constant from for a flocculation reaction. And next time we'll have some practice. I'll probably give you an in-class assignment to work a problem and to see where you can get with it, kind of as a participation sort of thing, and give you practice with tying these things together. So all of what we just looked at was this coagulation. That leads into us being able to flocculate our particles, to cause them to aggregate. So flocculation is a fancy term to say they're going to start sticking, right? You have one flock, which might be a few particles sticking together, or maybe we just say it's one particle. But when we flocculate, now they're starting to stick together and aggregate. So the right way to make this happen is to give them gentle mixing. Because if we have particles and we want them to stick together, if our water is too still, the only thing that can get them together is diffusion, and that's probably going to be too slow. They're almost never going to meet. We also don't want to shake it vigorously, because then if we did have a particle stuck to another one, we might break it apart with the shear forces, right? So we just want a gentle mixing, give them time to meet, but not so forceful that we're tearing them apart. So collisions, but no turbulence is best. What we're effectively going to do is going to reduce the number of particles. But we don't really care too much at this stage how many particles are there. We just want to increase their size. If we have 10 particles and they all stick together and we assume that their volumes are conserved, like we will assume that, then we've reduced the number of them, but more importantly, we've increased the size. So then they can settle in our sedimentation. Okay, so we're trying to reduce n over time. n being the number concentration of particles. The purpose is to increase their size. So we're going to track the number because we can do that with our rate constant stuff and our reactions in order to create these larger particles and then have some control over that. Okay, so the question becomes, well, how do we know the rate at which they're sticking together and how can we approach that mathematically? So we're going to have some rate constant K, and there's going to be a few factors going into it. One is probably already obvious, that mixing condition. Another is going to be this coagulation stuff. Have we destabilized them appropriately? And a third component is going to be, well, what fraction of my bottle of water actually has particles in it? Like, what volume of this is occupied by particles? Because if there's only like 2 tiny little particles in here, it's going to take a very long time before they meet. So each of these factors is going to go into the rate constant that we can use for how effective we are about getting these particles to stick together. So first of all, let's go into the mixing conditions. We will call G a mixing intensity. And we have a definition or a formula here for G as the square root of the power that we're putting into it divided by the viscosity of the solution, also divided by the volume of this flocculation basin. So you can imagine if I took a 1 horsepower motor, put a little propeller on it, and stuck it in an Olympic-sized swimming pool, yeah, it'd be mixing, but not a huge amount. If I did the same thing in a 1 liter bottle, that thing would be very, very well mixed, right? It would be way too much power for one little bottle. So the volume clearly has a play. The power clearly has a role. And if you've ever tried to, if you've ever bought, let's say, peanut butter, that's like the organic kind, and it's doesn't have like the vegetable oils added. It's just the peanuts, and it separates the peanut oil and all that. You try to mix it around. It takes a lot of effort to mix that, right? Or if you were to mix honey or something, it takes a lot more effort to mix that than it would take to mix water. So the viscosity also clearly has some importance. So those are the terms, and we're going to keep the units pretty straightforward. Watts are typically, that's newtons and seconds, right? So, or joules, which is comes back to newtons, and seconds there. So we're going to leave G as a per second. So it's almost like you can think of like laps per second or something. It's the mixes per second. That type of thinking might get you there. We'll see why that works in a moment. So we're going to keep it in seconds and meters and kilograms. And that means when we take our volume here, we should have that in cubic meters. So probably the easiest way to think about what is this mixing intensity is to take a look at what happens when water is flowing across a surface, or a surface is flowing through water, and you get some sort of a gradient of velocity next to that surface. So right next to that surface, if water, let's say, is flowing this direction, you'll have some velocity component here. You've got some drag slowing it down, and it's just not very fast compared to the rest of the solution. So as you go a little further away from your surface, you will see an increasing velocity, right? And then you can take a line here and say, well, we have some sort of a gradient, and that's a gradient as a function of distance away. If we're just to say this is y direction, as a function of distance, our velocity term of the water is changing, right? And turns out that'll probably change in a linear fashion. And we'll call this change G. That's our mixing intensity. You can imagine if this is really, really, if the line was very sharp, that's a lot different than if the line was very steep, or steep versus leaning like that. So in the one case, your velocity is not changing much, small change in velocity per change in y, or a big change in velocity versus change in y. So this would be high mixing. It's a huge velocity gradient. Low mixing, or low G versus high G. And the reason, you know, we could write this out a little more mathematically to say the differential of the velocity versus differential of the y, that's essentially giving us units of 1/seconds, because it's distance per time divided by distance, right? And so that's where we are getting this seconds to the -1 mixing intensity term. All right, so this is just a kind of showing you physically what that would mean and why we have a per second term and all that. So this is one component. You'll have this equation on your formula sheet. So do make sure to put that in your memory as what do each of these components mean. This is a uppercase V. That's a volume term. So make sure you recognize that accordingly. So we'll get into the rest of the parameters for K and how we actually find K in just a moment, and we'll probably stop there. But before we get there, I want to take a moment to say what this looks like when we put it into practice. And maybe we'll stop after the slide anyway, I don't know. If we have several particles, let's say we have 1, 2, 3, 4, that's 5, 6 particles. And then that's what we start with, and then we end with 2 particles that are each 3 particles in size, 3 of the originals in size. We can describe this in terms of n. Let's imagine this little circle is a bit of volume. Well, this would be the initial number, would be 6 particles per volume. And this final one at some time later is 2. And we're going to assume these are kind of stuck together and those are individual particles there. So we have 2 particles per volume that we ended with, right? So what we're doing, and these are larger. In fact, they're 3 times larger. So what we're doing is we're saying when we say our reaction rate is going to look something like this, dN dt equals negative Kn. Well, it depends on how many there are. So n to the 1 power, that means it's first order. The n is decreasing because they're sticking together, so that means it's a decay reaction. We now recognize you've been equipped to deal with first order decay reactions. You know something about that from the first few lectures. Now, when we put this into practice, what we will look for is actually something pretty interesting. We could look at the number remaining, the fraction remaining, or we could invert it. So n over n naught is often what we look at, right? So the fraction remaining. That's not actually as useful this time as n naught over n, which is how many of the initial ones are in each of the final ones. So pause on that and hear what I just said. This is telling us how many original particles are in each of the final ones. Because if we know something about the size of the initial ones, this lets us know the size of the final ones. Okay, so this is actually almost all it's about. So how many initial particles in each final particle or aggregate or whatever you want to call it, final aggregate. And in this case, you know, from this example, n naught over n is 6 over 2, which is 3, right? And so now we know the volume is 3 times the initial volume. And given that we probably know something about the diameter of the particle, then we can solve for the diameter of the next particle if we assume it just merged and became a new sphere. Okay? So that's what we will practice next time, and we'll continue there on Thursday.